students. So welcome back to my video lectures on the fourth chapter, that is chemical bonding and molecular structure of 11th standard. So we were solving MCQs on this chapter. Let us continue with the MCQs. Okay, so I think we have solved around 40 questions. Okay, let us continue with the rest of the questions. Okay, so what was the last question? The last question was, I think, this was the last question, isn't it? So we had missed one thing. So here we have to have hydrogen peroxide, and this was the correct answer. Okay, so this was the question from All India Pre-Medical Test 2005. Okay, so in the last video we have completed up to 41 questions. So now let us continue with the next question, that is 42nd question. And what is that 42nd question? Which of the following molecules has trigonal planar geometry? Okay, which of the following molecules has trigonal planar geometry? Trigonal planar geometry means regular geometry. So we have IF3, that is iodine tetrafluoride, phosphorus trichloride, ammonia, boron trifluoride. Okay, students, let me take the questions. Trigonal planar geometry, direct question. If you know the examples, if you have thoroughly read the examples, they can indirectly say. But if you don't know, if you have not learnt the examples, look at here, it is All India Pre-Medical Test 2005. Those who are looking really serious about NEET examinations, by looking at this question you would have told the answer. What is the answer? Of course, trigonal planar geometry means boron trifluoride, boron trichloride. They are all trigonal planar geometry. But if you don't know, if you are not able to memorize the example, then you have to look into each and every options. Just check the hybridization of each and every option, and then you have to find what is hybridization for each and every option, and then you have to find the answer. It's a long process. That is why I always tell to my students, wherever you find examples are most important. Examples are most important because at least you can expect 5 to 6 questions in your NEET examination, which is direct questions will be on the examples. This is also one such question wherein they have directly asked you a question regarding trigonal planar geometry. Direct question. If you just know within less than 2 or 3 seconds, you can just say, it is boron trifluoride, and you can just mark the answer in the OMR sheet, isn't it? But if you don't know, you have to sit and solve. Okay, how do you solve this? Trigonal planar geometry. Okay, for trigonal planar geometry, okay, for trigonal planar geometry, hybridization has to be sp2, isn't it? Trigonal planar geometry. I told you boron trifluoride is trigonal planar, and trigonal planar geometry is for regular geometry. What do you mean by regular geometry? Okay, regular geometry means central atom is surrounded only by bond pairs, only by bond pairs of electrons, only by bond pair of electrons. Trigonal planar geometry. I told you boron trifluoride. How is the structure? Boron trifluoride, just like this. Okay, boron trifluoride or trigonal planar geometry. Yes, here the bond angle is how much? The bond angle is 120 degree. Each bond angle is going to be 120 degree. Bond angle is 120 degree. And what is the hybridization of boron? sp2 hybridization. sp2 hybridization. Look here, boron is surrounded only by bond pairs. Bond pairs. There are no lone pairs at all. Okay, hence what type of geometry is it? It's a regular geometry, boron trifluoride. Okay, even if you calculate hybridization, okay, didn't I tell you how to calculate hybridization? What is the formula that you will use to calculate hybridization? What is the formula? Hybridization, yes, H is equal to half of B plus M minus C plus A, isn't it? Okay, so if you get the value of 2 sp, 3 sp2, 4 sp3, 5 sp3d, 6 sp3d2, 7 sp3d3, 7 it is sp3d3, isn't it? Okay, sp3d3, exactly. So if you take boron trifluoride, okay, the central atom is boron. Okay, boron belongs to 13th group. So total number of valence electrons is 3. Okay, for 13th group, the total number of valence electrons is 3. Okay, half of V means total number of valence electrons. M means number of monovalent atoms. Okay, fluorine is monovalent, isn't it? There are 3 fluorine atoms, three monovalent atoms. Is there any, okay, C means total positive charge, A means total negative charge. Is there any positive charge or is there any negative charge? No. So 0, 0. So 3 plus 3 is 6. Half of 6 is 3. 3 means what hybridization? sp2 hybridization. sp2 hybridization means what geometry? Trigonal planar geometry. Trigonal planar geometry. Okay, yes, this is with respect to option D. Even if you take option A, B, C, okay, I think you will get, let us check the hybridization for option A. For option A, IF3, okay, where, okay, look at the state of hybridization for hydrogen. Sorry, iodine is the central atom here, half of. Iodine belongs to halogen family. Halogen 17th group. 17th group, 7 valence electrons. So V is 7. Number of monovalent atoms, fluorine is monovalent atoms, so there are 3 fluorine atoms. Positive charge 0, negative charge 0, 0. 7 plus 3 is 10, half of 10 is 5. 5 means what type of hybridization? Yeah, it is, okay, 5 means sp3d hybridization. sp3d hybridization. Okay, but what is the geometry of IF3? What is the geometry of IF3? Huh? Okay, any idea with respect to the geometry of IF3? Yes, sp3d hybridization. See, we know students, for sp hybridization is linear. Okay, sp2 trigonal planar, sp3 tetrahedral. Okay, yes, sp3d, okay, trigonal pyramidal, bipyramidal, okay, sp3d2 octahedral, okay, sp3d3 pentagonal bipyramidal, pentagonal bipyramidal, isn't it? sp3d3 pentagonal bipyramidal. So we are getting the hybridization of IF3 as sp3d. Do you mean to say the geometry is trigonal bipyramidal? No. Even though the hybridization of IF3 is sp3, it is not trigonal bipyramidal. Because I will tell you why. Because it is not a regular geometry, it is irregular geometry. Only if it is regular geometry, okay, only if it is regular geometry, then you can say that sp3 hybridization corresponds to trigonal bipyramidal. But it is not a regular geometry, it is irregular geometry. Because here the central atom iodine is surrounded by both bond pair as well as lone pair. It is surrounded by both bond pair as well as lone pair. Why? How? See, iodine, 17th group, 7 valence electrons, isn't it? Okay, out of 7 valence electrons, it has used only 3 valence electrons to form bond with fluorine, and the remaining 4 electrons are lone pair of electrons. So iodine is surrounded both by bond pair as well as lone pair. Therefore, it is irregular geometry. If it is irregular geometry, please look at the table that I have made you to write. Okay, 2 lone pair and 3 bond pair. 2 lone pair and 3 bond pair. Okay, the geometry is quite different for IF3. You look into that table. Okay, is that simple? Okay, next, if I go with option B, PCl3, check the hybridization of the central atom. Hybridization is equal to half of. Phosphorus belongs to nitrogen family, 15th group. 15th group means 5 valence electron. So number of valence electrons is 5. There are 3 chlorine atoms. So chlorine atoms are monovalent. So the number of monovalent atoms are 3. Any positive charge? No. Any negative charge? No. So 5 plus 3 is 8. Half of 8 is 4. 4 means what? sp3 hybridization. sp3 hybridization. Okay. Now next one. Okay. Next one. What is it? Okay. Option. Yes. Option. So C. Let us take option C. Ammonia. Ammonia. Okay. Yeah. Calculate the state of hybridization of the central atom. Half of nitrogen, 15th group. So 5 valence electrons. There are 3 monovalent atoms, no positive charge, no negative charge. So 5 plus 3 is 8, half of 8 is 4. 4 means what hybridization? sp3. So the question was for trigonal planar geometry. Trigonal planar geometry means sp2 hybridization. So we have got only one option with sp2 hybridization. Okay, that is BF3. So therefore the answer is option D. Option D. Clear? Okay. Okay, that's it. Very simple question. Yes. Next question, students. Okay. Which of the following would have a permanent dipole moment? Permanent dipole moment. We have boron trifluoride, okay, then silicon tetrafluoride, sulfur tetrafluoride, and xenon hexafluoride. Which of the following would have a permanent dipole moment? Okay, yes, boron trifluoride, silicon tetrafluoride, sulfur tetrafluoride, and xenon tetrafluoride. Okay, so All India Pre-Medical Test 2005. Boron trifluoride. See the structure of boron trifluoride. Boron trifluoride. Okay, this is how the boron trifluoride is supposed to be, right? We know dipole moment is always directed towards a more electronegative atom. Okay, remember that point. Dipole moment is directed towards a more electronegative atom, towards a more negative atom, isn't it? Towards a more electronegative atom. That means dipole moment is a vector quantity. Why it is a vector quantity? Because it has both vector quantity because it has both magnitude as well as direction. It has both magnitude as well as direction. So dipole moment is a vector quantity. So dipole moment is directed towards a more electronegative atom. So we have boron and fluorine. Fluorine is more electronegative than boron. So that the dipole moment of this bond is towards what? Fluorine. How do we represent a dipole moment? We represent a dipole moment with an arrow mark, okay, and a tail at its end. This is how we represent a dipole moment. Okay. So the dipole moment of this bond is towards fluorine. Well, the dipole moment of this bond is towards fluorine, and the dipole moment of this bond is towards fluorine, because fluorine is more electronegative than boron. See, okay, I hope you have learnt it in physics, parallelogram law of forces. See, this dipole moment is towards this direction, and this dipole moment is towards this direction. What will be the direction of the net dipole moment? The net dipole moment will be in this direction, isn't it? Okay, the net dipole moment of these two dipoles will be in this direction, correct? The net dipole moment of these two dipoles. So this dipole moment is in this direction. This dipole moment is in this direction. The net dipole moment of these two dipoles will be in this direction, correct? Okay, now observe here. Okay, this is one dipole and this is one dipole. Don't you think these two are equal and opposite dipoles? Yes, these two are equal and opposite dipoles. When these two are equal and opposite dipoles, they cancel each other. Am I correct? These two are equal. The resultant dipole of these two dipoles is in this direction, and there is one dipole in this direction. So these two are equal and opposite dipoles, therefore they cancel each other. So what is the net dipole moment of boron trifluoride? The net dipole moment of boron trifluoride is going to be what? 0. The net dipole moment on boron trifluoride is 0, because it has equal and opposite dipoles which cancel each other, okay. Okay, next, silicon tetrafluoride. So the net dipole moment on this molecule is 0. Very nice. How about silicon tetrafluoride? Yes, silicon tetrafluoride. Okay, can anybody tell me? Silicon tetrafluoride. It is actually tetrahedral structure, but I have written it like that so that you'll be able to understand. Again, fluorine is more electronegative than silicon. Okay, so the dipole moment is in this direction. Okay, here also fluorine is more electronegative than silicon, therefore the dipole moment is in this direction. The net dipole moment of these two dipoles will be in this direction, isn't it? Correct? Okay. The net dipole moment of these two dipoles will be in this direction. Okay. So what is the dipole moment of this bond? In this direction. The dipole moment of this bond is in this direction. So the net dipole moment will be in this direction. Okay. Again, these two are equal and opposite dipoles. These two are equal and opposite dipoles. We know equal and opposite dipoles will cancel each other, and hence the net dipole moment will be equal to 0. So what is the net dipole moment on this direction of this molecule? It's going to be 0. Okay, correct. Yes. Next, sulfur tetrafluoride. Sulfur tetrafluoride. Look at here. Sulfur tetrafluoride. Okay. Yes, be careful now. Sulfur tetrafluoride. Sulfur has one lone pair of electrons. Sulfur has one lone pair of electrons. Sulfur belongs to which group? Sulfur belongs to 16th group. 16th group means 6 valence electrons. Please listen up here. 6 valence electron. See, out of 6 valence electrons, it has used 4 valence electrons to form bond with fluorine. Therefore the remaining 2 valence electrons are lone pair of electrons, isn't it? Sulfur belongs to 16th group. 16th group means 6 valence electrons. Okay, so sulfur, out of 6 valence electrons, it has used 4 valence electrons to form bond with 4 fluorine, and the remaining 2 valence electrons are lone pair of electrons. Am I correct? Is that simple? Okay, now what is the dipole moment? Here fluorine is again more electronegative. Fluorine is highest electronegative of all. Fluorine is the highest electronegative element of all the element in the entire periodic table. Do you agree with my point? Yes. So that means to say fluorine is more electronegative than sulfur. Hence the dipole moment will be in this direction. Fluorine is more electronegative than sulfur. Therefore the dipole moment is in this direction. Okay. The net dipole moment of these two bonds will be in this direction. Okay, no doubt in it. Yes. Again, fluorine is more electronegative. The dipole moment is in this direction. Yes, the dipole moment is in this direction, and the net dipole moment will be in this direction, isn't it? Again, these two are equal and opposite dipoles. They cancel each other. Okay, but don't say that the net dipole moment of this molecule is 0. No, because there are also lone pair of electrons. Okay, there will be dipole moment towards lone pair of electrons. Okay, all these two dipole moments have cancelled. They have cancelled, but there is dipole moment towards lone pair of electrons, but that is not going to cancel because there is no other dipole moment in the downward direction, in the opposite direction. So therefore this dipole moment will not cancel. Let us take the dipole moment to be equal to x dpi. We don't know the value, let us keep it as x dpi. Okay, so what is the dipole moment of sulfur tetrafluoride? It is x dpi. And what is the net dipole moment? The net dipole moment is towards lone pair of electrons. All other dipole moments will cancel. All other dipole moments will cancel, but there is a dipole moment towards lone pair of electrons. So there is a dipole moment, and I have taken it as x dpi. Okay. Now let us go with xenon hexafluoride. Xenon hexafluoride. Okay. So what is the dipole moment of this direction? It is x dpi. Okay. Yes. That means it has a permanent dipole. There is a net dipole moment, and the dipole moment is towards lone pair of electrons, and all other dipole moments have cancelled, completely cancelled. Now let us talk about xenon tetrafluoride. Remember, xenon belongs to noble gases, noble gas family. Okay, noble gas family means 18th group. 18th group means how many valence electrons? Yes, 8 valence electrons. 8 valence electrons, isn't it? Look at here. Out of 8 valence electrons, xenon will form 4 bonds with 4 fluorine atoms. Okay, 4 fluorine atoms like this, and the remaining 4 will be lone pair of electrons like this. Okay, the remaining 4 will be lone pair of electrons. So out of 8 valence electrons, xenon has formed 4 bonds with 4 fluorine atoms, and the remaining 4 will be lone pair of electrons. Again, go ahead with the dipole moment. So here it is in this direction, here it is in this direction. Therefore, what will be the net dipole moment? The net dipole moment will be in this direction. Okay, correct. So again, here the dipole moment is in this direction. The dipole moment is in this direction, and the net dipole moment is in this direction, correct? Okay, so these two are equal and opposite dipoles. These two are equal and opposite dipoles. Therefore, they cancel each other. I have told you that there will be dipole moment towards lone pair of electrons also. That means here there is one lone pair. So that means the dipole moment will be in this direction. Here also the dipole moment, lone pair of electrons, the dipole moment will be in this direction. Again, these two are equal and opposite dipoles. They will also cancel each other. So what is the net dipole moment on xenon tetrafluoride? The net dipole moment on xenon tetrafluoride is again 0. The net dipole moment on boron trifluoride is 0. The net dipole moment on silicon tetrafluoride is also 0. The net dipole moment in xenon tetrafluoride is also 0. But there is a net dipole moment in sulfur tetrafluoride. The question is, which of the following would have a permanent dipole? Yes, of course, the answer is option C, sulfur tetrafluoride. Sulfur tetrafluoride. Any doubts? Okay. Good. That's extremely correct. Yes. Okay. Students, let us go with the next question. In which of the following molecules all the bonds are not equal? In which of the following molecules all the bonds are not equal? Is it ClF3 or BF3 or aluminium trifluoride NF3? In which of the following molecules all the bonds are not equal? Okay, is it ClF3, boron trifluoride, or AlF3, or nitrogen trifluoride? We will take up this question later. Okay, yes. Now again the question is on dipole moment. the electronegativity difference between nitrogen and fluorine is greater than that of nitrogen and hydrogen, yet now read out the question very carefully because it has been asked in All India Pre-Medical Test 2006. The electronegativity difference between nitrogen and fluorine is greater than that of nitrogen and hydrogen, yet the dipole moment of ammonia is larger than the dipole moment of nitrogen trifluoride. What is the dipole moment of ammonia? It is 1.5 d, and the dipole moment of nitrogen trifluoride is 0.2 dBi. This is because, okay, we know students, okay, dipole moment increases with increase in electronegativity, isn't it? Dipole moment increases with increase in electronegativity. Increase in what? Electronegativity. Increase in electronegativity. Okay, dipole moment increases with increase in electronegativity. So they have given ammonia and nitrogen trifluoride. Look here students, ammonia NH3, yes, pyramidal structure with one lone pair of electrons, and nitrogen trifluoride, it is also pyramidal structure with one lone pair of electrons, pyramidal with one lone pair of electrons. Here the dipole moment is given as how much? 1.5 dBi, whereas here the dipole moment is 0.2 dBi. That means dipole moment of nitrogen trifluoride is less than the dipole moment of ammonia. Okay, see students, I have given you a statement there. Dipole moment increases with increase in electronegativity. Dipole moment increases with increase in electronegativity. We know, okay, fluorine is more electronegative than hydrogen. That means, okay, here the electronegativity difference between nitrogen and fluorine is more than the electronegativity difference between nitrogen and hydrogen. But still, the dipole moment of nitrogen fluoride is less than the dipole moment of ammonia. Why? You have to justify this. I am telling you that as the electronegativity increases, the dipole moment increases. Of course, fluorine is more electronegative than hydrogen. That means to say nitrogen fluoride would have a more dipole moment than the dipole moment of ammonia, but it's wrong. Actually, the dipole moment of nitrogen trifluoride is less than that of ammonia, even though fluorine is more electronegative than hydrogen. Why? How do you substantiate this? Very simple. Use the logic. It's such a simple question. Very simple question. You have to use a logic. Okay, how? Look here. See, okay, no doubt. Okay, so here, what is the direction of the dipole moment? Direction, okay, always, okay, dipole moment is directed towards okay, more electronegative atom, and lone pair of electrons, and what? Lone pair of electrons. Always the dipole moment is directed towards more electronegative atom and lone pair of electrons. That means the dipole moment is directed towards more electronegative atom, or it is directed towards the lone pair of electrons. Okay, yes. So here, what is the direction of the dipole moment? Nitrogen is more electronegative than hydrogen, therefore the dipole moment is towards nitrogen. Here also the dipole moment is towards nitrogen. The dipole moment is towards nitrogen. So what is the net dipole moment of these three dipoles? It will be in the upward direction, is it? Okay, so this and this will add up, and the net dipole moment will be in this direction, correct? But look at here, there is also lone pair of electrons. There is also lone pair of electrons. Let us say the net dipole moment of these three dipoles is x d by. Okay, x d by, correct? X d by, isn't it? There is also lone pair of electrons, and we know the dipole moment is directed towards lone pair of electrons. The net dipole moment of these three dipoles is in the upward direction, and also there is a dipole moment towards lone pair of electrons. Then let us call the dipole moment towards lone pair of electrons as y d by. Y d by. Therefore, what will be the net dipole moment? The net dipole moment is equal to x plus y d by, isn't it? X plus y d by. Okay, that means the dipole moment of these three dipoles, the net dipole moment of these three dipoles plus the dipole moment of the lone pair of electrons will add up. Therefore, the net dipole moment will be x plus y d by. X plus y d by. Are you all able to understand my point? The net dipole moment of these three dipoles is in the same direction as that of the dipole moment towards lone pair of electrons. Therefore, they will add up x plus y d by. Okay. Whereas if you come to nitrogen trifluoride, fluorine is more electronegative than nitrogen. So therefore, the dipole moment is towards fluorine. The dipole moment is towards fluorine. The dipole moment is towards fluorine, correct? So what is the net dipole moment of these three dipoles? The net dipole moment of these three dipoles will be in the downward direction. Okay, the net dipole moment of these three dipoles will be in the downward direction. Let me call that as x d by. Okay, x d by. But there is also dipole moment towards lone pair of electrons. Let me call that, okay, yes, dipole moment as y d by. But these two are in opposite direction. These two are in opposite direction. These two are in opposite direction means they do not add up. They will cancel, is it? Therefore, the net dipole moment of this nitrogen trifluoride is x minus y d by, isn't it? It is going to be x minus y d by. Here the two dipoles, the net dipole moment of these three dipoles plus the dipole moment towards lone pair will add up to give x plus y d by, which is 1.5 d by. Whereas in nitrogen trifluoride, the dipoles of these three dipoles is in the downward direction and the dipole towards lone pair is in the upward direction. Therefore, they cancel to a certain extent. Hence, the net dipole moment will be x minus y. That is why the dipole moment of nitrogen trifluoride is less than the dipole moment of ammonia. In case of ammonia, the net dipole moment as well as the dipole moment towards lone pair, they will add. Whereas in nitrogen trifluoride, the net dipole moment and the dipole moment towards lone pair, they will cancel. They will cancel. Therefore, the net dipole moment of nitrogen trifluoride is less than the net dipole moment of ammonia. So, what is the correct answer, students? Okay, in ammonia, okay, let us take option A. In ammonia as well as nitrogen trifluoride, the atomic dipole and bond dipole are in the same direction? No. In ammonia as well as nitrogen trifluoride. In ammonia, yes, the atomic dipole and the bond dipole are in the same direction. Whereas in nitrogen trifluoride, they are in the opposite direction, isn't it? Okay, this and this are in the same direction. Whereas in nitrogen trifluoride, this and this are in opposite direction. So option A cannot be the answer. In ammonia, okay, next option. In ammonia, okay, the atomic dipole and the bond dipole are in the same direction, whereas in nitrogen trifluoride, these are in opposite direction. Is that correct? Yes, of course. Yeah, okay, in ammonia, yes, in ammonia, the atomic dipole and the bond dipole are in the same direction. They are in the same direction. Okay, whereas in nitrogen trifluoride, the atomic dipole and the bond dipole, they are in opposite direction. They are in opposite direction. That is why the dipole moment of ammonia is less than the dipole moment, the dipole moment of nitrogen trifluoride is less than the dipole moment of ammonia. Therefore, very simple question. So what is the answer? The answer is very simple. It is option B. Option B. Are we clear? Excellent. Yeah. Okay. Yes. Let us move on to the next question. Did you understand? So if the dipoles are in the same direction, they will add up. If the dipole moments are in opposite direction, they will cancel. they will cancel. Please remember that point. Okay. Yes, students. Yeah, next question. Okay, which of the following species has a linear shape? Which of the following species has a linear shape? Linear shape. Okay, linear shape means what? What type of hybridization? SP hybridization. The hybridization has to be SP. Okay, which of the following species has linear shape? Is it NO2 minus, it is supposed to be like this, NO2 minus SO2, or NO2 plus and O3. Okay, so that means you have to calculate just hybridization, that's it. Okay, yes, you have to get SP hybridization. Okay, for SP hybridization the shape is linear. Okay, so is it NO2 minus or SO2 or NO2 plus or O3? Can we calculate hybridization? Come on guys. Okay, hybridization formula, half of, okay, V plus M minus C plus A, half of V plus M minus C plus A. Okay, so for SP hybridization, the hybridization, you should get the value of H to be equal to what? 2. If H is equal to 2, then the hybridization is going to be SP. If the hybridization is SP, then the shape is going to be linear. The shape is going to be linear. Okay, simple. Now let us calculate the hybridization for NO2 minus. Option A, NO2 minus. So hybridization H is equal to half of, okay, so which is the central atom here? Nitrogen is the central atom. Always the less electronegative atom is the central atom. Okay, nitrogen belongs to 15th group, 5 valence electrons. Okay, so plus, okay, M means number of monovalent atoms. Oxygen is divalent, not monovalent, so number of monovalent atoms is 0. Minus cationic charge, that means positive charge, 0. Anionic charge, 1. Anionic charge is 1. So 5 plus 1 is 6. Half of 6 is 3. That means it is not linear. It is not linear. For linear, you should get H value has to be 2. Okay. So but you are getting 3. Therefore, it is not linear. 3 means SP2. SP2 means trigonal planar shape. Okay, yes, next option. Let us take SO2. Okay, SO2, calculate the hybridization of SO2. Here sulfur is less electronegative than oxygen. Half of sulfur belongs to 16th group. 16th group means 6 valence electrons. Number of monovalent atoms 0, because oxygen is not monovalent, oxygen is divalent. So the number of monovalent atoms is 0. Positive charge is 0. Negative charge is 0. So half of 6 is again 3. 3 means it is not linear. It is not linear. Is that correct? Okay, simple. Yeah. Next, let us go with NO2 plus. NO2 plus. Calculate the hybridization. H is equal to half of, okay, nitrogen, 15th group, 5 valence electrons. Number of monovalent atoms, no monovalent atoms, because oxygen is divalent atom. So there are no monovalent atoms, 0. Minus, there is one positive charge, that means minus 1. Negative charge is 0. 5 minus 1 is 4. Half of 4 is 2. Look at here, we are getting H value to be equal to 2. If H value is equal to 2, what type of hybridization? SP hybridization. SP hybridization means what shape? Linear shape. Linear shape. Is that correct? Linear shape. So what is the correct answer? Option C. Let us check with option D also. Let us check with option D. Ozone. Okay. O3. Yes. Hybridization. Oxygen. There are 3 oxygen atoms. Take one of the oxygen atom as the central atom. Half of. Oxygen means 16 group, 6 valence electrons. No monovalent atoms, 0. No cationic charge, 0. No anionic charge, 0. So 6, half of 6 is 3. 3 means what type of hybridization? sp2 hybridization. Okay. But we want sp hybridization, and sp hybridization is found only in NO2 plus. So the answer is option C. Okay. Simple. That's great. Okay. Yes, students, next question. Okay, which of the following is not a correct statement? Okay, which of the following is not a correct statement? The electron deficient molecules can act as Lewis acids. The canonical structure is not a real, have no real existence. Every AB5 molecule does in fact have square pyramidal structure. Multiple bonds are always shorter than the corresponding single bond. Okay, so which of the following is not a correct statement? So option A says electron deficient molecules act as Lewis acids. The canonical structures have no real existence. Every AB5 molecule does in fact have square pyramidal structure. Okay, multiple bonds are always shorter than a corresponding single bond. Okay. Yes, which of the following is not a correct statement? Yes, every AB5 molecule does in fact, okay, have square pyramidal structure. Every AB5 molecule, okay. The canonical structure have no real existence. The electron deficient molecules can act as Lewis acids. Multiple bonds are always shorter than the corresponding single bond. Okay, yeah. Okay, students, let us say, okay, look here, the first option, if I go with option A, the electron deficient molecules can act as Lewis acid, of course. So we have Lewis acid base theory, isn't it? Lewis acid base theory. Okay, Lewis acid base theory. What do you mean by a Lewis acid? Okay, any substance which accepts electron pairs. That means Lewis acids are electron pair acceptors. Is it correct? Okay. Whereas Lewis base means any substance which donates a pair of electrons. That means Lewis bases are electron pair donors. Electron pair donors. Lewis acids are electron pair acceptors, whereas Lewis bases are electron pair donors. Okay, if a species has to accept electrons, if I am accepting electrons, that means I am electron deficient. Okay, so if I have rich electrons, if I am electron rich, why do I accept electrons? Or if I have sufficient amount of electrons, why do I accept electrons? If I am accepting electrons, that means I am deficient of what? Electrons. So, okay, Lewis acids are electron deficient species, electron deficient, where, okay, I am donating electrons. When do I donate electrons? Only when I have excess of electrons, isn't it? I will donate electrons only when I have excess of electrons. That means electron pair donors, bases are electron pair donors. When do they donate electrons? Only when they are electron rich. Okay, so acids, Lewis acids are electron pair acceptors. They will accept electron pairs because they are electron deficient. Lewis bases are electron pair donors. Why do they donate a pair of electrons? Because they are electron rich. So according to the first option, the electron deficient molecules can act as Lewis acids. Yes, electron deficient molecules will accept a pair of electrons, hence they act as what? Lewis acids. So this is correct. Canonical structures have no real existence. Yeah. For example, benzene, if you write the resonance structure of benzene, how do you write? Okay, yes. See, this is one resonance structure of benzene. This is another resonance structure of benzene, isn't it? Correct? This is another resonance structure of benzene. Okay, so we will write the resonance hybrid as, yes, we will write the resonance hybrid like this, correct? So these two are called as resonating structures, or else they are also called as canonical structures. Resonating structures, or else they are also called as canonical structures. Canonical structures. Canonical structures. Are you getting it? Yeah, okay. So we know, yeah, canonical structures do not have real existence. They do not have real existence. So option B is also correct. Okay. Yes, option D says multiple bonds are always shorter than the corresponding single bond. Of course, multiple bond. Triple bond is shorter than double bond. Triple bond is shorter than double bond. Double bond is shorter than single bond. That means single bond is will always have, okay, longer bond length than double bond than triple bond. As the multiplicity increases, bond length will also increase. So that means option D is also correct. So which of the following is not a correct statement? We have only one option with or not correct statement. Yes, of course it is option C. Every AB5 molecule need not have square pyramidal structure. They need not have, it is not compulsory that all the AB5 molecules will have square pyramidal structure. So which is incorrect statement. Yes, option A is correct. The electron deficient molecules can act as Lewis acid. Yes. The canonical structures do not have real existence. True. Multiple bonds are shorter than the corresponding single bond. Triple bond is shorter than single bond. Double bond is shorter than single bond. That is also true. But not all the AB5 molecules, okay, it is not necessary that all the AB5 molecules have square pyramidal structure. So the incorrect one is option C. Next question. Okay, yes, next question students. Okay, now the question says, in which of the following pairs the species are isostructural? I have told you what is isostructural in the previous videos. Okay, in which of the following pairs the two species are isostructural? What do you mean by isostructural, students? Isostructural. Okay, isostructural. Iso means what? Same. Okay, that means species having same structures. Species having same structures or same shapes, they are called as isostructural. And when will you say that the two species will have same structure? They'll have same structure when they have same hybridization. Only when they have same hybridization, they have same structure. If they have same structure, then those species will be called as isostructural species, isn't it? They will be called as isostructural species. Is that correct? Yes. So that means our job is very simple. Just find the hybridization of each and every pair here and just see which of the pairs have the same hybridization. If they have same hybridization, they have same structure. If they have same structure, they are referred as what? Isostructural species, isn't it? Yes. So let us find out the hybridization. We have SO3 2 minus and NO3 minus. Option A. Let us take option A. SO3 2 minus and NO3 minus. Let us calculate the hybridization. Yes, half of V. Okay, what is the formula to calculate hybridization? H is equal to half of V plus M minus C plus A. Remember that formula always. How many times I have used that formula? I don't know. Okay, so in my previous lecture videos, how many times I have used the same formula? Yes. Okay, I think right now at least you should be, okay, that formula should be at the tip of your tongue. Okay, yes, if you revise the question, revise the videos again and again, you will become more and more thorough with that. Okay, yeah, so use that formula. H is equal to half of, okay, sulfur is the central atom. Always I have told you, the less electronegative atom is the central atom. Okay, so we have to calculate the hybridization for the central atom. Okay, we have to calculate the hybridization for the central atom. Here sulfur is the central atom, here nitrogen is the central atom. Oxygen is more electronegative than sulfur, oxygen is more electronegative than nitrogen. So less electronegative atom, please take it as the central atom. Okay, so calculate the hybridization. Half of sulfur 16th group, 6 valence electron plus M monovalent atoms. Any monovalent atoms attached to the central atom? No monovalent atoms, because oxygen is divalent, so 0. Plus positive charge, minus positive charge 0. But there are two negative charge, that means plus 2. V plus M minus C plus A. C stands for positive charge, A stands for negative charge. Positive charge cation, negative charge anion. Okay, so there are two positive charge, so it is plus 2. So 6 plus 2 is 8. Half of 8 is 4. We are getting hybridization of this to be 4. 4 hybridization 4 means sp3. sp3, isn't it? Now how about this molecule? H is equal to half of, okay, central metal atom is nitrogen, 15th group, 5 valence electron plus M. No monovalent atoms, 0. Okay, no positive charge 0, but negative charge is 1. 5 plus 1 is 6. Half of 6 is 3. 3 means sp2 hybridization. So hybridization is different. Different hybridization means different structure. Hence they are not isostructural. Correct? Yes, exactly. Now let us go with the next option. BF3 and NF3. Yes, students, BF3 and NF3. Come on. Okay, BF3. Okay, here which is the central atom? Boron. Here which is the central atom? Nitrogen. Fluorine is more electronegative than boron. Fluorine is more electronegative than nitrogen. Fluorine is the highest electronegative atom of all the element in the entire periodic table. Okay, yes, come on, calculate boron. Half of boron 13th group means 3 electrons, 3 valence electrons plus M monovalent atoms. Yes, fluorine is monovalent atoms, 3. Positive charge 0, negative charge is 0. 3 plus 3 is 6. Half of 6 is 3. 3 means sp2 hybridization. Okay, how about for nitrogen trifluoride? H is equal to half of nitrogen 15th group, 5 valence electrons. Okay, 3 monovalent atoms. Positive charge 0, negative charge is 0. 5 plus 3 is 8. Half of 8 is 4. 4 means sp3 hybridization. So this is sp2, this is sp3. This is trigonal planar, this is tetrahedral. Therefore, different hybridization, different structure. If they have different structure, they are not isostructural. Understood? Okay, next option C. We have BrO3 minus and XeO3. BrO3 minus and XeO3. Come on, calculate the hybridization. H is equal to, here which is the central atom? Bromine. Here which is the central atom? Xenon. Okay, so we are calculating, remember, we are calculating the hybridization of the central atom. So hybridization is half of bromine, halogen family, halogen 17th group, 7 valence electrons plus monovalent atoms 0, positive charge 0, there is 1 negative charge. Okay, so 7 plus 1 is 8, half of 8 is 4 means what? sp3 hybridization. Now going on to this, calculate hybridization. H is equal to half of xenon 18th group means 8 valence electrons, monovalent atom 0, positive charge 0, negative charge 0. Okay, half of 8 is, yeah, we got 4 means what? sp3 hybridization. Look at here, BrO3 minus is sp3 hybridized, XeO3 is also sp3 hybridized. sp3 hybridized, sp3 hybridized, same hybridization. Same hybridization means same structure. Same structure means they are isostructural. So which of the following pairs, the two species are isostructural? Yes, it is BrO3 minus and XeO3. Okay, they have same hybridization. This is also sp3 hybridized, this is also sp3 hybridized. Same hybridization means same structure. Same structure means they are isostructural. Very simple question. So it is option C. Okay, yes students. Yeah, let us quickly go with few more questions quickly. Yes, come on. Next question. Yes. Well, what is the next question? Quick. In which of the following the hydration energy is higher than lattice energy? This question we basically learn this type of question in S block elements also, but the concepts is explained under chemical bonding, don't worry. Okay, in which of the following the hydration energy is higher than lattice energy? Hydration energy is higher than lattice energy. Okay, yes. What is hydration energy, by the way, students? Hydration energy. Hydration energy. What do you mean by hydration energy? The amount of energy released when an ion is solvated. When an ion is solvated. What do you mean by solvated? Surrounded by solvent molecules. Okay, surrounded by what? By solvent molecules. Surrounded by solvent molecules. Okay, it is the amount of energy that is released when an ion is solvated. Ion is solvated means it is surrounded by solvent molecules. Okay, look here, when I dissolve sodium chloride in water, no doubt sodium chloride will split to give Na plus ions and Cl minus ions. Here each Na plus ions will get surrounded by solvent molecules. Which is the solvent here? Water is the solvent. So each ions will get surrounded by water molecules. This is what we call solvation. We call it as what? Solvation. When the ions get surrounded by solvent molecules, energy is released, and the amount of energy that is released is called as what? Hydration energy. The amount of energy that is released when an ion is surrounded by water molecules, that is when an ion is solvated, when an ion is surrounded by solvent molecules, that amount of energy is called as what? Hydration energy. That amount of energy is called as hydration energy. Okay, remember one thing, hydration energy is inversely proportional to ionic size. Is inversely proportional to what? Ionic size. Hydration energy is inversely proportional to ionic size. Smaller the ionic size, more will be the hydration energy. That means smaller the size of the ion, more number of solvent molecules will surround that ion and more energy is released. Therefore hydration energy will be high. So hydration energy is inversely proportional to what? Ionic size. Smaller the ionic size, more will be the hydration energy. More will be the hydration energy. Are we clear, students? Yes. Now, based on this idea, let us solve this question. In which of the following hydration energy is higher? Okay. Yes. Hydration energy is higher means smaller size. Hydration energy is high for smaller ionic size, isn't it? Okay. So students, the options are magnesium sulfate, okay, radium sulfate, okay, strontium sulfate, barium sulfate. Okay, let us arrange them in the increasing order of ionic size. So, okay, so upon magnesium sulfate, upon ionization, it's going to give magnesium ions and sulfate ions. Okay, radium ions will give radium ions plus sulfate ions. Okay, strontium ions will give strontium ions plus sulfate ions. Barium ions will give barium sulfate will give barium ions and sulfate ions. So sulfate ion is common, let us leave this. Let us consider magnesium, radium ion, strontium ion and barium ion. Now the group we have magnesium, then strontium, barium and then radium. We know down the group ionic size increases, isn't it? Down the group ionic size increases. That means radium ion is bigger than barium ion, barium ion is bigger than strontium ion, strontium ion is bigger than magnesium ion. So which ion has least ionic size? It is magnesium. Smaller the ionic size, more will be the hydration energy, isn't it? Smaller the ionic size, more will be the hydration energy. So in which of the following the hydration energy is higher? Yes, it is of course for magnesium sulfate. It is of course for magnesium sulfate. Understood? Yes. Okay. Cut it. Okay. Yes. Okay, students. I hope you have understood all the MCQs on this chapter. Okay. Thank you.